So let's take a look. I hope you have taken a look at this problem by yourself. The lambda, which is the number of unit fails each hour, number of units that fail each hour, can be calculated a lot of different ways, but the general idea is number of failure divided by the total unit operating hours. If you break it down, here's units tested multiplied by number of hours tested. Okay, the numerator is number of failures. So, I mean, this formula doesn't quite capture how you exactly calculate the lambda. Therefore, we need an example here, okay? So we are testing 10 units. So ideally, if nothing fails within 100-hour period, the total hours we tested is going to be 1,000 hours. However, that is not the case, because 4 units will fail at each of those hours. Okay, so the number of hours we have tested in this case is going to be 6 multiply 100. So 4 units failed at the end of these hours, and the rest of the 6 units actually lasted a total 100 hours. Okay, that is the total number, that is the total unit operating hour here. And then of course, your numerator here is number of failure, which we experienced before. You will get the failure rate when you're done with the calculation. So this is solution. If you look at the Excel solution, this is all these units, right? We tested 10 units. Each unit, 6 hour, 35 unit, so forth. All of them lasted for 100 hours. And these are the cumulative testing hours. There's nothing but 6 plus 35 becomes 41. In other words, you're adding up all these testing hours, okay? So eventually, your total testing hours of 776, and you divide 4 with 776, that will give you this failure rate. Okay, it means our lambda 0.00515. Okay, you have 0.005 failure per hour. Okay, per hour. And what is MTTF? Our lambda, our calculation tells us this is 194. So you have to wait in general, you have to wait 194 hours to experience the very first failure. Okay, so this is, as usual, the Excel solution. This is a visualized version of it. So we got our lambda, we got our mean time to fail. Okay, I hope you're clear at this point. Let's continue to move on. So here I'd like to discuss something very interesting, what we call as bathtub curve of reliability. So if you look at this overall shape of the failure rate, in the early phase of product life, you will see a unusually large number of failure rates in the beginning. Okay, what we call as early life. And once it stabilizes, what we call as a useful life will start. So during the useful life, the failure rate is usually truly random. It's fairly stable. Okay, it's not unusually high like in the early life. So if you think about, so those products, there were some way somehow slip through the internal external quality checkpoint and released to the market, and consumer bought it, and before they use it, you usually experience a lot of failure. Like a new car you bought, new car you bought this year, and you experience some kind of problem in transmission and brake. How come this can happen? This is new car. But that is because you are experiencing early life failure rate. Okay, but once it stabilizes, let's say you have driven like 1 year or so, it enters the useful life, and you won't experience as many failures as in the early life. Okay, and then once the warranty period finishes, or the so-called useful life finishes, and then it's entering the wear out period, and you will also experience fairly high failure rate. So this is a very famous bathtub curve of reliability model. This conceptually helps you understand the different failure rate during the different phase. Okay, so I think if you're a manufacturer, you need to focus on reducing the early life failure rate, because after the early life, the failure rate is usually pretty random, pretty stable. So let's say early life is measured at 200 hours, and you can use 200 hours as a lab testing time to try to study the failure rate during the early life. This also resembles the human life. Okay, you'll see a lot of baby dying when they're very young. We call it as what? Seed. I forgot what's the full name of it. And then once you enter your adult age, you're very likely to die. Okay, but once you become very old, the chance of your failing is also very high. So we also call it as a mortality rate, mortality rate or mortality reliability model, or in this case, we're calling it as a bathtub curve of reliability. Okay, so this is just a conceptual demonstration. And let's move on to reliability function. Okay, reliability function. So in this case, instead of just calculating one reliability or reliability in one single point, we'd like to we'd like to obtain the function. Okay, as you know, function look like this or like this, like this. These are all function, and the advantage of using function is you can sometimes visualize it fairly conveniently. Okay, also once function is obtained, you can easily calculate y based on x. So the simple example was the Taguchi loss function is another function, right? So you got the k, and then you can plug in whatever value of x in order to calculate the expected loss. So that is the beauty, that is the convenience of the function. So in here, we're not technically letting you come up with the all the components of function. Rather, we'd like you to develop the overall pattern of reliability. So you'll know what I'm saying as we go together. So consider following exercise or example here. A tire manufacturer needs to determine a mileage warranty policy for a new line of tire. Okay, they have a new product line. Suppose that mean life of tire is 60,000 miles with a standard deviation of 1,000 miles, and it is normally distributed. These are all the lab test results. Have an average life of 60,000 miles with a standard deviation of 1,000 miles, and it is normally distributed. So our question number 1, please develop a reliability function. Okay, and based on the reliability function, answer the following questions. What proportion of tire will survive after 62,500? In other words, what is the survival rate on what is survival rate? What is the probability of survival for the 62,500 mileage of the tire? Okay, in other words, what is the likelihood that this tire will still functioning on this particular mileage point? Okay, so number 3, in order to control the number of within warranty service to less than 3% of total tires, how much mileage should the firm seek to cover? Okay, so they need to determine a mileage number so that they want to only service less than 3% of total tires. Let's say this is 60,000, and the standard deviation was like 1,000. Okay, assuming that this is the aggregation of all the tires they release to the market, right? So each tire will have different failure rate. These failure rate are assuming random. They only like to service less than 3% of total tires they have released to the market. And then what is this point of x? Yeah, this is very similar to some of the normal distribution problem we have solved in the past. So let's move on, take a look. Let's first develop a reliability function. So here, this is a solution. This is our textbook version of the reliability function, okay? Instead of letting you come up with an explicit mathematical formulation of the reliability function, it's letting you develop a, array of numbers like what you're seeing here. So you enumerate all these tire life. We're not listing from mileage 1 all the way to mileage 100,000. Okay, we're only enumerating those very likely numbers here. Okay, so based on this distribution right here, they're also normal. Therefore, you can calculate what is the chance that a tire will fail within 55,000 miles. Okay, you can also calculate probability of tire that will fail within 56,000 miles, and so forth. So these are all the probabilities. So assuming that your tire has average life expectancy of 60,000 miles, it is nearly impossible that you will be experiencing any failure when it is still 55,000 miles. Okay? Assuming that your tire's average life expectancy is 60,000, there will be less than 1% chance that you will be experiencing failure in 56,000 miles, and so forth. This follows all the same interpretation. So what's this number tells you? Assuming this is, okay, I'm not going to repeat it again. So almost certainly you will experience failure when your tire is 66,000 miles. Okay? And this is a reliability, which sometimes can also be called as a survival probability of survival. So it's nothing but 1 minus the failure rate. 1 minus failure rate. Let's take a look how we can interpret this guy right here, okay? So for example, let's interpret this. When a tire has a mileage of 59,000, and the chance that it will experience failure within this period is nearly 16%. 16%. Okay? And of course, the other 84% of chance is that it will not experience failure. Okay? So this is a probability that it will survive pretty well beyond this point, 59,000. Therefore, we also call this probability as a survival rate at 59,000. Does that make sense? Okay, so this is all the Excel solutions. You can take a look at yourself. We've used all these formulas forever, and this is nothing but 1 minus this particular value. You will get survival rate. I'm sorry, yes, survival rate. So you always need to calculate the failure rate, and then you can do 1 minus to obtain the survival rate, which is your reliability at that point. Okay, so if you look at this curve, the blue curve here is the failure. This is actually the true reliability function. This is a true reliability function. Although there's no math, the function sometimes can be in mathematic form, function sometimes can be in visual form. So this is a visual format. Okay, this is telling exactly what we have discussed right here. So for example, if you look at the 60,000, you'll have equal failure rate, equal survival rate, because that is average. Okay, but if you look at 61,000 here, 61,000, the survival rate is fairly low, but the failure rate is fairly high because it's past the average life expectancy of 60,000. That's what we can tell by looking at the curve. Okay. Looks like I need to, I think I can wrap it up. Okay, number 2 I've already addressed because almost the video has to be finished within 15 minutes. I only have like 10 seconds. So question number 2 has already been addressed, right? Proportion of tire will survive after 62,500 miles. So you can look up the table, you can also calculate like this.